Oh my God. Chewbacca over here. Shook up my fleece. That's what I'm Hey, Potter. I haven't. Are you talking about the guys who look like
Guillermo?
Actually look like Ewok?
Guillermo? Dorothy?
Oh, I know what you're talking about. I know exactly who walks like this. He's the only one walks like this.
Monica?
I see that guy. I haven't seen him around for a while.
No, he's still here.
He's still here?
All right, guys. It's kind of funky. I wonder if I actually I wasn't talking about the smell. I don't smell the funkiness, so maybe what I'm talking about is that more people are over there where it's a little bit darker. So I wonder if I turn all lights down a little bit, if everybody would spread out. It's very strange. I like them. Nobody's in there except for you guys. Are there any questions from homework? Yeah.
I have a question. Number 56?
In section
2.7?
So this is page 205. All right. So the question here is find now, I didn't make a point of saying this last time. Hopefully it kind of came out of this, but this symbol does not mean flip. It doesn't mean reciprocate. Like the inverse is not just 1 over the original function. Cool. How do I go about doing this process, finding the inverse function? Good, so you bring back the y first. And the whole idea of inverse functions is it takes the inputs and the outputs and it switches them. It wants to take the outputs back to what the inputs would have led to that output. It wants to take it back to where it was to begin with. So this is just me. I just draw the little line for myself telling me I'm doing something funky. That's the word of the day. I'm not doing something algebraic to this necessarily. I'm using a concept. So I switch the x and y. And then I do what? Yeah, I start to solve for y. So be careful the way you say it. What is the opposite of fifth power? Fifth root. So you take a fifth root of both sides. This fifth root cancels that. Fifth power. You're almost there. Kind of makes sense that if the original problem had a couple powers on it, the inverse should have a couple roots on it. So that's what's going to end up happening. What could I do next? Personally, I always hate when the thing I'm trying to solve for is negative, so I just and then you just take what? Take a nap.
Yes.
Sounds good, man. One last step. Cube root. Yeah. It's a little worried there. So then F inverse will be this monster there. as gruesome as we thought it should be from the beginning. What's happening to the x? It's being cubed, and then eventually it gets raised to the fifth power. So I should expect a couple of roots to happen in the inverse. The opposite stuff should happen. To me, one of the most interesting functions, inverses, which you'll only hear math teachers say that phrase. Find the inverse of that. So you switch the x and the y, right? And then you multiply the y up and divide the x down, so it just switches back. Right? When I want to try to solve for y, wouldn't I multiply by y? And divide by x? So I end up getting y equals 1 over x again. And it kind of makes sense. How do I undo somebody flipping a number? Flip it again, right? So this is one of the few functions who is its own inverse. Which must mean what about the graph? The graph of a function and its inverse, how should they be related? Yeah. The graph of a function and its inverse, the mirror has to be right here, right? Y equals x. So if a function is its own inverse, it itself must be symmetric to this. In fact, y equals 1 over x looks like this. So sure enough, if I flip it over the y equals x line, hey, it's the same thing. So any function that's already symmetric to y equals x is its own inverse. I don't know if that's just neat to me or what, but it's all right if it is. I'll deal with it. Yeah.
Number 48.
Oh yeah, good. This is another. We did one sort of like this the other day, but this is a little bit worse. That one there, right? We're in 2.7, or which section are we in? 2.7. Yeah. That should be the 148. Or do you have the funky international edition? I think so, yeah.
Yeah.
Is it a function like that, or is it something else? Tell me what it is.
It's 2x plus 5 under x minus 7.
So this is underneath?
Yeah.
All right, so same idea as that. So we'll do this problem, and it's like this one. I like it, because I do too many of your homework problems for you. So how do I find this guy's inverse? Same question, right? Find the f inverse. Yeah, the process can't change. Just the thing I'm dealing with changes, but the process can't change. You still bring back the y, and you still flip them. The only problem, and this shouldn't be a big problem anymore now, what was a big problem for us was once we do this, how many y's do we have running around? But do you remember what we did the other day? Right, we had a problem like this. Are there really 2 y's running around? No, there's one. I just haven't grouped them and sucked it out yet. Right? GCF that bad boy out. So you multiply that guy up. Get everything with y in it on one side, and then GCF it out. So try to do that one. I did. I do that sometimes. So it's like this number 48 for most of us. Would be nice to Lathe on this problem and do his problem.
And that's it? That's where it stops?
No, I asked. You just hang out. I asked them to try it out before I keep going. I know you've tried it out, so you're like, what do you want me to do? suspense is killing me here. xy minus 7x. So you get everything with y in it on one side. So I want to move that 7x out of there. Move that 2y over here. Cool. And then, like we said, there's not really two y's. There's just one y that somebody distributed. How's that? Is that? Well, that's almost as ugly as this inverse type of process can get. And that's not even that bad. Just get all this stuff with what you want on one side, take it out, divide by what you don't want, you're done. This inverse process is really not that bad. Yeah?
Can you do number 80?
Is that always going to happen where it's just like the 7 and 2 switched off?
There's some generalizations you can make. If you really felt up to the task, you could find the inverse of this. Just to prove what you thought, right? So I'm not sure what percentage you would actually attempt that on your own. Maybe I'll make that extra credit on the test.
Yeah.
Hey, now, see? I like that. I say the magic words extra credit, so I get more interested. So if I gave you this function, could you find its inverse? Yes, you don't worry too much about it. I know A, B, and C, D are in there. Who cares? They're just symbols, going to go for the ride. So this wouldn't be that big of a deal. Then you can make some generalizations about something in this form. I like it. Cool. So any other questions? I think I was about to. Who was I about to? Yeah. 80. That's right. Okay. Let's see. Let me just give you an idea. I want to do this whole problem. So this is f, and they want you to graph f inverse. It's a strange reaction. So who can remind me? This is kind of like the very first problem I think we did with inverses, or one of the very first. You're just going to feel visually what would an opposite function look like, given some original function. So if the original function goes through 0, 1, we can start kind of collecting. If f goes through 0, 1, f inverse has to go through 1, 0. If the original function goes through 4, 6, 6, 4. And then you can get some other point from over there. I just want to get you started on this problem. So now I can start graphing these points. It's got to go through 1, 0. And it's got to go through 6, 4. You do it, Jeff. There it is. So you can see that's the mirror, and then it's going to cross through this mirror here, right? I mean, it's kind of nifty if you graph the original one and on top of it graph the new one, and you see the symmetry. Again, it might just be me, but still a good thing to look at. So this would be the beginning of it. Now you get that last point, wherever that last piece, that kink, wherever it goes, plot its mirror, and it should go across right there. Is that cool? Yeah. So obviously, I mean, inverse functions are stupid important. The minute you started learning how to solve an equation, you were talking about inverse functions. They just didn't say inverse function. The reason that we bring it up now like that is because we start talking about some funky functions. So we have to know this idea a little bit more in depth so we can attack these really weird-ass functions and create their inverses.
So that's the solution?
That's the beginning. Sorry. There's one more point somewhere over there that I just wasn't interested in enough. But you guys, whatever point that is, graph the mirror, right? Same way. I don't want to do the whole problem for you. Get a little more than half the problem for you, so I think it's all right. Any other questions from homework? All right, good. All right. I'm an optimistic fool, so
Are we getting out at 2:30 again?
What was that?
Are we getting out at 2:30?
Oh no, I've set a precedent now.
There's another game.
They're not. Not like that. You're gonna say something. You watched that strongman competition, Jeff? It's on tonight. No. That's funny.
Yes, and
Hey, anybody hear about the? I haven't even looked into this too deeply, but did anybody hear about the huge impact on Jupiter that an astronomer noticed?
oh yeah.
Have you seen that? There's actually video. If you go search Jupiter impact, there's video of this. It's an Earth-sized explosion on the surface of Jupiter. They're not sure. I haven't seen the latest if they've have any theories about it. Obviously, must have been some kind of a meteorite or something.
I heard that they estimate it happens about 10 times a year, and it's just one of the things that comes along with having such a big gravitational pull.
Oh yeah. But the interesting thing about this one is it was observed. I mean, space, even our own solar system is huge. Somebody has to be kind of watching all the time to see something like this. And it reminds me of, like, how long ago was it? Anybody in here into space at all? Astronomy? A little bit? Comet Shoemaker-Levy, if I say that, does that mean anything? That was the first comet. It slammed into Jupiter in 7 pieces, so they could watch it hit the atmosphere and they could see the resultant thing and they could interpret some things about the interior of the. It was neat. So just Google that, Shoemaker-Levy. It's actually exactly how it sounds. Shoemaker-Levy, if you happen to remember. Right. All right. Anyway, sorry. This is really freaky. We stop to think any second something can hit us and that's it. No big movie. No Bruce Willis going to save our ass. Let's see. Where do we leave off? I think there was here. We're going to do a problem together. One of the word problems from section 3.1. In case you didn't realize, there are word problems in section 3.1. And here's one of my favorites. Number 76, page 231. Pictionary up here. So let's say you have this 30-inch wide piece of metal, and you're going to try to make a gutter out of it. Right, like a gutter go around the top of your house. So you're going to bend the sides in by an indeterminate amount. You don't know yet. You're not sure how far you want to bend it in. Obviously, you don't want to bend it in at 15 inches, because then you just fold the thing on itself. Not a very effective gutter. So somewhere before 15 inches. And what you want it to do is to have the largest possible cross section, so it's able to contain the highest amount of stuff, be it water or whatever. Leaves, unfortunately, so you got to get it there and clean it up. Right? So you want this cross-sectional area to be maximum. Now I'm giving you a major hint that people often forget. This is a very classical problem. fact, very often in calculus, we'll even go one step further. We'll bend up the sides and make a little box out of this thing. So cut some corners out, just like a pizza box. But what we have to do first is something called modeling. And it's actually something you've done before. Anytime you've done an algebraic equation from a word problem, you've modeled. Modeling just means writing the equation that describes what's going on physically. So we got to figure out the equation, obviously, for the area of this thing. Well, how tall are these sides? X. Is very cool. You fold them over, and if I pick it up and look at edge on, there it is. Right? Fold these over, pick it up, look at it, straight in, there it is. So obviously they're going to be X long, however long I choose to bend it in. And how long is this here?
30 minus 2x.
Beautiful, 30 minus 2x. And I kind of gave it away when I put the x on both sides, but when people look at the picture in the book, they forget there's a second x. There's a second side you had to turn up. So it's not 30 anymore, it's minus x minus another x, so minus 2x. So trust me, this is another reason that people die in like 178 or 180 when they hit the word problems in either of those courses. They can't model the situation. They can't figure out how to write the situation in an equation. And you take steps to get there. You do exactly what I just did. You kind of tell yourself what they tell you. They give you this picture, that's nice, and then you try to start labeling the sides of this picture so you don't forget anything for the area. People that try to get through the problem very quickly and don't really write themselves down much to help themselves out, they're the ones that get weird-ass answers, like x should be -3. And I love it when they just turn it in. Okay, could you show me how to do that, please? So what would the area, that cross-sectional area, what would that be? How do you get that? Nothing too major here.
X
Nope.
times 30 minus 2x.
Yeah. Just length times width. Nothing major. Doesn't matter. There's no top to the poor little dude. That's fine. So what do you think this means to be maximized then? What would this look like if I graphed it? If we bring this x through, what would that look like?
Parabola.
Parabola. In fact, more specifically, a parabola that's facing down, which makes sense that it has a maximum. And I keep talking about it. I know several of you are going into calculus. So when you get to calculus, you'll have problems that aren't just parabolas. For us, we have to deal with parabolas. Because we can certainly find the maximum point. What's that point also known as? Vertex. In calculus, we could find max and mins for all of these. Right now, we have no freaking clue how the hell to find those. We can approximate them. We can cheat and do it in the calculator, but we don't know how to do it mathematically yet.
Okay, I get that why you have the 30 minus 2x, but where did the other x come?
The area. So this 30 minus 2x is a length.
Yeah.
Now, what does the problem ask me to work with? It says to maximize the area. So mathematically, I have to work with the area function.
But if that's x on the sides, how is that like proportional to the width of the middle?
What's the area of this rectangle? Don't worry, it didn't have a top. Who cares? So how much stuff could fit in there? What's the area? A times b. So x times 30 minus 2x. Just multiply the sides.
Because you didn't close. You didn't close the top.
Yeah, don't worry about the top. It's fine.
Yeah, but I'm saying like, is that supposed? I know that's not meant to scale, but I mean like, if that side, the sides are x long, it's just like it doesn't make sense why.
Well, okay. So now you're worried. And there's several. If I barely turn the edges in, then I'd have something like that, right? If I barely turn the edges up, which I don't know how. It's really difficult to do. You ever work with nothing? Just a little all the way down. It looked like that. Not a very good gutter, right? More effective for San Diego.
Oh, good. You're bringing it. Oh, okay. Ah,
Okay,
gosh,
cool.
I'm so. I know what's going on.
If you go to the other extreme, you could do like that.
Okay, I know.
Yeah.
I know what's going on.
That runs pretty deep, and it would keep out, maybe keep out some leaves. I don't know. That'd be nice. They get blown away, but okay, cool.
Yeah. Sorry.
So the whole point of this is the hard part of these problems, and it's not even a really hard part, but it is the one that gives us the most trouble, should be setting this thing up. the minute we have the quadratic thing set up, how do I find the vertex? What's the shortcut to find the vertex?
Switch them
Yeah, x equals negative b over 2a.
Yeah.
What's b?
30.
Good. It's just out of order. Don't say it's 2 just because it's second. ax squared plus bx is just out of order. So it'll be negative 30 over twice negative 2.
Negative 4.
Oh, okay, on the bottom. Sure. So 30 over 4. 7.5. Cool. So that tells me how far to turn each side up, right? Cool. So if I ask you, so that's how far each side, x equals 7.5, that's how far I have to turn each side up. What will the area be?
7.5, 13.
So 2 ways you could do that. And I certainly wouldn't blame you to not plug 7.5 in there. Because there's a much easier way to do it. If that's 7.5, 30 minus twice 7.5 is 15. So it'd just be 7.5 times 15. And whatever the hell that is. Cool, cool, cool. One 12.5? No. Is it 112? Yeah. Square inches. Was that cool?
Why did you choose 15?
Say again?
Why did you choose the 15?
Oh, if that side's 7.5, this side is 30 minus twice 7.5, right? So twice 7.5 is 15. 30 minus 15 is 15. Because if I bend in 7.5, where did I put there? If I bend in 7.5 on both sides, how much did I leave on this side? 15. Cool. You could just, exactly, you could just plug it into the equation. That's your area equation. So if you'd rather, you could just plug it in there and just let the calculator spit it out. No problem. What happened? Oh, thank you. Cheers.
When do you upload the videos?
They're up.
When would you upload this one?
Oh, today I have to leave immediately, so I can't do it in my office, but I'll probably upload it tonight from my house.
Sometimes you normally do it every day?
Yeah. Yeah.
Didn't you get 112? 25?
Yeah, 7.5 times 15. Or plug in 7.5 here, right? 30 times 7.5 minus twice 7.5 squared. Yeah. So what does that mean? If I bent that in any other length, what would be true about the resultant area? It would be less. There you go. Of course, that's the maximum area. So that's another way to kind of check yourself. Make x 8, and then this would be 14, right? 8 times 14 is 102, 112. I don't know what it is.
112.
Thank you, 112, which is a little bit less than that, right? So this is the maximum area. I love it. Yes, sir.
See where you got that 15 after the next area, on the next area.
Here. Oh, so let me do this up here. One way we could do this is to go back to the picture and say this is x, so that's 7.5, and this is 30 minus twice x. So 30 minus 15, 15. And then we just multiply those together. Or we have an area function right there. It says if we change x, the area will change. So we can do 30 times 7.5 minus twice 7.5 squared.
Which would give us 112.5.
Yeah, better. If it doesn't, we're in trouble. And of course it will. Because I don't know if you guys realize, these are the same thing. I mean, this is what you get when you multiply that side by that side. So of course if I multiply that side by that side, I should get the same number no matter how I do it. Plug the x in first or plug the x in at the end. It's got to come out to the same number. Cool. How do you feel about that so far? So yes, there are word problems. They're not nearly as vague as some of the ones you've seen in the past. And they should all end up at some quadratic function so that you could find the vertex. Okay. So what we're going to do today is going to do, I'm thinking we should be able to get up through 3, 4. Yeah. And the nice thing with 3.2 is we've already talked about a little bit of what's in 3.2. Somebody help me out though. Remind me, what is that? What is a polynomial? Poly means many, yeah. So you could have, specifically, you could have monomials, binomials, trinomials, and then after that they said, screw it, it's many. Right? And what does a nomial refer to? Term, I love it. So many terms. So some examples could be like 4x squared plus 5x minus 1. There's a classic, here's one that people forget. 11. That's a polynomial. Hell yeah. To be a polynomial, you have to have this form. Let me see if I can make this make any sense at all. So you can be as large of a power as you want, as long as your powers are whole numbers. With me? So you can go up, you can get x to the 500 billionth minus 7, x to the 497 millionth, As long as your powers are all whole numbers. And what does that do for you? What are fractional powers? What are those introduced? Fractional powers can be rewritten as what? Roots. And roots have limited domains very often, not always, but many of them do. You with me? Also, whole numbers can't be what? For example, they can't be fractions, but they also can't be negative. Cool. So, and if I had an x to the negative 1, what is x to the negative 1? 1 over x. And that would have a limited domain. You with me? So it seems to be saying that limited domain over and over, and the fact that this does not have that. So this is defined for every possible value of x. Okay, cool. So that sounds like a test question for some of you guys. This is a polynomial y. All these are 0 for it. These are all coefficients, by the way. Except for this guy, it's not 0, it's 11. Now some of you guys are like, well, where's the variable in there? Well, there's there. What's x to the 0 power? 1. Isn't 0 a whole number? Yes. So just constant by themselves are polynomials. They're very boring polynomials. When you graph them, right? Okay. They're like dead polynomials. This is really sad. They have no perspective. Now something else about polynomials. They have to be what's called continuous. So polynomials, domain is all reals. They must be continuous. Graph must be continuous and smooth.
Domain what?
All real numbers, yeah. That's the R with the extra. You guys know that means all reals. It means real numbers. Graph must be continuous and smooth. Continuous, I can't pick my pencil up and go somewhere else. And smooth means it can't be like this. That's not smooth. That's a cusp. That's like a really kinky point right there, right? It's not smooth. How are we doing so far? Okay, cool. So polynomials are just freaking awesome. They're really nice things. You want to have polynomials to work with because they're really nice. What's something else we know about polynomials that I've actually said before in this class, I think? If it's got a third power, how many times could it turn? Twice at most, right? So if it's the highest power is n, it can have at most how many turns? N minus 1, 11. Which is kind of why it makes sense that if the highest power is n, we're going to fill this in. If the highest power is n, then there are n solutions when it is equal to 0. Now those solutions could be real or complex. So we're going to focus on the real for now, and the complex is coming up soon. How are we doing?
The what?
If the highest power is n, then there are n solutions when it is equal to 0. So for example, x squared minus 4x plus 3 equals 0. Now remember, since there are definitely n solutions, but some of them can be complex. So I can actually kind of reword that. At most, how many real solutions are there to this? 2. And of course, how do you find the solutions? Factor, yeah, good. So x minus 3, x minus 1, x 3, 1. So that's exciting. Then somebody could say, and I would not blame you at all if you said, well, what about this? There must be 2 solutions. They could be complex or real. There are no complex answers to this, and you could argue something here in a minute. How do you factor this thing? X minus 2 a couple times, right? So what's the answer? X equals 2. Not plus or minus. Negative 2 would not make the answer 0. I like this. I like this. So you guys are trying to tell me what the other answer is. Here's the kind of lame thing about this. 2 just shows up twice. Right? You guys kind of with me? So, I mean, you got to give math some leeway. If it happens to have the same answer twice, math is not wrong. It's just that one is repeated. Ooh, there's still 2 solutions. They just happen to be the same. No. So I want us to understand that right now for later. Yeah.
Is it supposed to be like x equal 2x equal negative 2? Or?
Definitely not. If I plug a negative 2 in here, it makes negative 4 squared, which is 16, not 0. So there is only one number that makes this work, 2, but it shows up twice. Cool. There's no other answer to this besides 2. Are we good with that? Because when I take a square root, plus or minus 0 is still 0. There's not more than one answer. Okay. Cool, cool, cool. Now, something else about these things. All of these are going to have what basic shape? Yeah, basic U shape, right? Take that off there. There we go. Now, what's really interesting about the higher powers, think about it for a second. So x squared we all know that that's x squared there. Oh, come on, Jeff, doesn't have to be perfect. 1/2 squared is 1/4, right? You guys with me? There must be some reason why I said that. If it was x to the 4th, what's 1/2 squared? I mean, 1/2 to the 4th power. What is 1/2 to the 4th power? 1/16. So the interesting thing about all the even powers on x have the same look, but the higher powers have a flat bottom because they don't rise as quickly, right? 1/2 squared is 1/4. 1/2 to the 4th power is only 1/16. So this will look more like, well, that's kind of extreme, but it'll have a flat bottom. And if you take it out to x to the 100th power, it kind of starts looking like our gutter did. X to the 100th power, if you did that on your calculator and zoomed in a little bit to here, it would look like this. It's kind of crazy. It's still curved, but the curve is so sudden here. Okay. All right, is everybody semi with me? That's cool? Okay. Oh, so of course the other side of the coin is what all these look like. Basic, what I call cubish shape, which is this here. Whoop. So I will use the adjective, the cubish. We should all know what x cubed looks like. It looks like that. So anything that's to an odd power like that should have a cubish shape to it. And the same kind of thing applies for x to the 5th, x to the 7th. This middle part gets a lot flatter for the same reasons. Okay, cool. Now what happens with something like this here? Yeah, it just flips. It almost doesn't matter which way you want to say it flips, because this is the same as that. So it's either in with the x or not. So imagine if you flip it around this way, it comes out like this. Flip it around that way, it comes out like this. That's kind of nice. You can't go wrong there. And of course, we all know what happens when I put a negative in front of these guys. The u just turns upside down. All right, Jeff, that's great. We all know that. Okay, good. So what that leads to is, I really want you guys to get this. Find something like this here, for example. That graph is more than likely going to be semi-funkadelic, right? Just to use a very technical term. What must it do when x gets really big? I love when I say it. When x gets really big. So how do we represent that in math? Let me show you. This will help those who go in the calculus. You get a little preview of what some stuff you're going to see. Another way to say x gets really big is x approaches infinity. X goes to or approaches infinity. So think about it. When x gets really stupid big, or your favorite adjective, which part of this is the most important, is the most dominant part? X cubed. So all the other stuff barely matters then. Right? It's like having $1 million and somebody gives you $1. Like, oh wow, thanks. This stuff doesn't really come into play much. So when x gets really big positive or x gets really big negative, the shape of this graph has to match the shape of this. Let me say that again. Since these parts really don't come anywhere near being the influence of this guy when x gets really big, it's got to have the same shape at the ends as a cube does. So this is what's called, incredibly enough, end behavior. This leads us to the idea of end behavior. So if I had something like what would this guy's end behavior be? Yeah, so at the end it's got to look like an upside down parabola. And here's how I want it represented. Because I don't know what the hell it's doing in the middle. When x is small, these parts become much more important. So it can do all kinds of weird shit in the middle. But at the ends, when x gets really big, positive or negative, it's got to be shaped like a parabola, like a downward parabola. So the end behavior would be this. Cool. So in the middle, who knows? I know how many turning points can it have? At most, 3. So it could go turn once, twice, 3 times. See, then it would match back up with its end behavior. With me? Some guys might realize what we're getting into already. We're getting into the graphing hell part of the semester, right? Where we just analyze the hell out of functions and how it relates to the graphs. And I understand students are always thinking, I got this damn calculator. There's all this shit for me. But then you don't get any intuitive feel for it at all, and you die in calculus. This calculator can't explain stuff to you. What? So what about this here? Be careful, what are you looking for? You're looking for the highest power. Of course, I'm a little evil here. You should expect teachers to put stuff out of order sometimes. That's the highest power, so the end behavior should be up on both sides. So the end behavior would be bam. Yes.
So that's how we solve it?
That is just the step of what's the end behavior. That's it, right? This is not a true problem in itself. This is just like part B in a 5-step process of what is the end behavior. Cool. Okay? So, let me ask you guys, when I go to graph something, when I go to graph a function, what's the good place to start? What do I want to find first? Do I just start making an XY table and drive myself crazy, plugging in points forever? Vertex if it's a quadratic. What if it isn't? What if it's a 6th power? So you start with this. It's not a bad idea. Start with the end behavior. I like it. But then you also find the zeros and the intercepts. I love it. So intercepts is a more general term. Zeros specifically are the x-intercepts. And also find the one y-intercept. Why do I know there's only one y-intercept? Because it's a function. It can't have 2 because then it wouldn't pass the vertical line test. Cool. So if I had this guy, which guy? I don't know. So first off, what's the end behavior?
Negative.
Cubish. So you can make yourself a little picture. So it's really nice because once you start doing this and we start connecting dots, you can kind of use the end behavior to make sure you're going in the right direction at the beginning and the end. It's kind of an overall format issue. Just double check that you end up like that. Or for you guys like that. How do I find the intercepts? Yeah, exactly. Y-intercept, x equals 0. If you make x 0, you get y 0. How do you find the x-intercepts? Set the whole thing equal to 0, so it almost always involves factoring this thing so you can see the parts. So how do I factor this thing here? Take an x out. Good first step. You're right in the first one. It's got to be positive big, so the middle term ends up positive. Doing okay? So I mean, it's sort of like a lot of things in math. We have all these disparate things we've learned. This kind of thing just puts them all into one problem. And they're all used to make a final graph result. So we get, for the x-intercepts, we get one we already knew, 0, 0. We get -7, 0, and we get 1, 0. Cool. Okay. Cool, cool, cool. So, one last little thing we can do for ourselves. So we're going to explain it. We're still doing that example. I just got to explain this last piece. And it's something we've done before. The one thing we're missing is, how can I put this together for you guys? So for a parabola, if it's down, then I know it's negative out here and it's positive in the middle. But if, in general, I don't know where necessarily it's going to be positive, where it's going to be negative. I know now these. We just figured out these here points, didn't we? So what have we done in the past that fills that in? Tells me where it's above the x-axis, where it's below the x-axis. Believe it or not, we've done something like this before. Where you make the number line and you do the pluses and minuses. Now you've also got the shortcut, which they explain a lot better here, which I'm also going to explain because I like the shortcut because it makes it quicker. But we'll do it both ways. So what are the zeros? They were 0, -7, and 1. So who remembers how to get this thing started? What am I looking at? And we're looking at this here function. So if I plug in like a 2, plug in a 2, what sign comes out? Yeah, positive, positive, positive. I love it. What do I have to plug in and investigate here? Or give me an example. There's an infinite number of things, but I could just plug in a half. When I plug in a half, it's positive, positive, negative. So it's negative overall. How are we doing? So can you start to see visually it goes through the x-axis here and up? It's below the x-axis here, right? You kind of start seeing what this thing is going to look like. It's going to be coming from below, go through the x-axis, and now it's positive over here. In here, I can plug in -1, negative, positive, negative. So overall positive, those two negatives cancel. And then I plug in like -8, negative, negative, negative. So it's negative. Now, who remembers the shortcut? Now they've done it the long-ass way. What's the preferred short-ass way? Yeah, each of these is to a first power, right? So each root would have multiplicity what? New term today. 1. They'll only show up once. So if it's got an odd multiplicity, it changes signs. If it's got an even multiplicity, like a parabola would, it doesn't change signs like a parabola would not, right? Parabola can't change signs at its root. It's got to stay on one side. You guys kind of with me? So that's why I went positive, negative, positive. And that just kicks so much ass, because then you just have to plug in one number. So if I plug in a 1, I mean, what do I do? A 2, and I get positive, I automatically can just start alternating negative, positive, negative. Which is really nice when you have like 7 zeros or something. Okay, how we doing? So we're going to finish this problem out, and then I'll show you a little more complicated example, and we'll just do it the multiplicity way, and then hopefully that will stick, so everybody can kind of do that method.
Can you repeat the power thing? Square?
If it's got a multiplicity of
1
that's odd,
okay. Odd power.
it'll go through. It'll change sign. If it's got an odd power from that root, it'll change sign. If it's got an even power, it won't change sign. Cool. So let's graph this thing here. Let's see. What do we know about this? The intercepts 0, 0. -7 and 1. And let's see. Who knows? I'm going to hold off on this for a second. Now, the end behavior kind of gets me started. One other thing we can do for ourselves is plug in just a few points, but now I can be smart about it. I don't know how high it gets in the middle here, do I? I know that it starts here and it goes through. How do I know that? Because it's negative here. It goes through, becomes positive, and it's got to come back down and go back through here. Are you guys with me on that? It's got to start down here. We know that from our end behavior. And also we know because it's negative, it's got to become 0 at -7. Now it's positive in here, and then it's got to turn back around and go through 0 and become negative for a little bit of time here, right? So if I could just get a feel for how tall this thing gets. So maybe if we plug in something toward it in the middle, maybe -4 and -3. So our graphs are not going to be monster perfect. So what first tells me that somebody's used a graphic calculator and copied is when it really, really looks nice and everything's perfect. Then I'm like, wait a minute. It shouldn't be nice and perfect. It should be close. So I need some kind of, I have no idea how tall to go here. So what would f of -4 be, for example? If I throw a -4 in, now I want to know the real output. It would be -4 times 3 times -5. And do you see why I didn't make my scale yet on my y-axis? I wasn't sure how large this thing was going to get.
How did you get the 3 and the 5? -5?
Plug a -4 in. So -4. -4 plus 7 is 3. -4 minus 1 is -5. And of course, what's that come out to be? 60. So one nice thing about this real quick is the fact that it's positive, thank God. I'm supposed to be positive there. Right? So kind of re-verification of that. And now I know about how tall to go. If you wanted to, you could do f of -3, which I guess I want to for some reason. -3 times 4 times -4, so that gets a little bit lower. So let's just do -4 goes, let's say make it 10, 20, 30, 40, 50, 60. So at -4, it's at 60. That is not necessarily the exact maximum, but that feels right. It at least gives us a rough sketch of this thing. That's all we need is a rough sketch. To find the true maximum mathematically, you would need calculus, which I will not teach. Now here, this probably doesn't go way far down, does it? I mean, I bet anything. But if we plug in 1/2, oh God, what do we get? 1/2 times, what is that? 1/2 plus 7, which is 15 halves, times -1/2. So that's like -15 divided by 8. So it's about -2. Are you guys with me? Again, I don't have to be perfect, so it's kind of nice. You can kind of approximate a few things. So it's about -2 here, whoops, which barely gets a scale of 10, so 2 would be way up here. I knew it wasn't going to be way the hell. How could it do that in that little bit of room there? Possibly could, but probably not. And what's going to happen after 1? It's just going to keep going. There's my end behavior. It's just got to keep going up like that, like a cube. So I'm basically done here. Now I can kind of do my rough sketch. So it starts negative, goes positive, goes up to about here, comes back down here, just a little bit underneath there, and goes up forever. Cool. Not too bad, right? Every piece of this is something we know. The hard part very often is just pulling it all to come together on a graph. We very often are going the wrong way somewhere.